Evaluation is one of the main techniques to produce valid data mining. There are several techniques to understand a structure from raw data. A choice needs to be made as to which data mining techniques should be used. A technique is needed to understand the operation of different data mining techniques. We then compare their relative performance. Evaluation is easier said than done. The problem. Starting with a training set, the easiest way to go is to run different machine learning algorithms, example classification algorithms, on that data and monitor the resulting accuracy. Unfortunately, the issue is not that simple. The resulting accuracy on the training set is not a measure of the real-world performance. If a large and representative training set is present that mimics the actual real-world data is present, then we can simply base our model on it. The problem lies when large quality datasets are lacking. An example to that is image classification algorithms that might need to be manually labeled. Example, an image with pixel values categorized into a type. Some algorithms predict classes, neural nets or KNN algorithms detecting a human, animal, or object. And others predict probabilities, Bayesian algorithms detecting that there is a 90% chance of that an ice cream would be sold if it is sunny. Each algorithm needs to be evaluated differently. Our focus in this video is classifiers. The main issue here is cost, which is the error of misclassification, detecting a positive example as negative or a negative example as positive. The main idea is to test a classifier on data that has not been utilized in the training of the algorithm. Machine learning can include two parts, basic setup and optimization. In such cases, three datasets are used: training, validation, and test sets. The validation set is utilized to increase the accuracy of a classifier's parameters or to choose a certain classification algorithm. The cross-validation set should not be similar to the training set in order to achieve better accuracy in optimization and selection. Cross-validation involves dividing the dataset into parts called folds. The process involves several iterations. In each iteration, the data is divided equally, and one of the folds is used for testing while the others are used for training. The goal is to have each fold tested. The default technique used to find the error of a machine learning algorithm is to divide the dataset into 10 folds. It is important to have the data randomly divided with equal class or label representation on each fold. The machine learning algorithm is trained on 9 of the 10 folds and then tested on the remaining fold. The procedure rotates this procedure over all of the remaining folds. This testing can inform us of an algorithm's error rate. Finally, we calculate an average of all the errors to get a general estimate. Example. Let us consider that we have 30 pictures of animals, cats and others. Next to each image, we have a label that identifies the animal, cat, as 1 or not as 0. We intend on utilizing a neural network to identify the inputted image, cat or not. A neural network is essentially a mathematical formula with coefficients and biases that get modified in a training process to give out high input 1 when the inputted image or other is desired, cat image in our case. The issue we need to optimize is the number of layers in the neural network. This can greatly affect classification accuracy. The aforementioned cross-validation technique is applied on neural networks of different sizes in order to choose the required model. In our case, each cross-validation fold is composed of 3 images. Each fold should be representative of the entire dataset. In our case, this means that it should contain at least one cat image. After we perform cross-validation on neural networks with 2, 3, and 4 layers, as an example, we compare the resulting error in each and then choose the model with the lowest error rate. The chosen model is expected to classify cat images better than the other setups.